So greetings everyone. As it's already 5, let us start today's live session. This is our 10th live session, and this course is being taught by Professor Sanjeev Sabadan, and I am TAing the course. Until now, we have seen the semiconductor physics, and at the end of the and later part of this course, we will also see a bit of circuits. So, continuing our discussion on the numerical solving or the assignment solving problems, previously we had solved the assignment uh, up to the question number 3. So this was the last question that we solved. So today we will be solving the question number 4 first. It states that we have some MOSFET, that's MOS capacitor with p-type silicon substrate, and the temperature is given to be equal to 300 Kelvin, and it is this is doped at acceptor with acceptor doping concentration of 10 to the power of 16 centimeter per centimeter cube. And this silicon dioxide, the oxide, this oxide is having the thickness of 55 nanometer. Also, we have been given the device area, and it is 2 into 10 raised power minus 3 centimeter square. And we have been told to assume the thermal voltage to be equal to 25.9 millivolts, and intrinsic carrier concentration is 1.5 into 10 raised power 10 per centimeter cube. So after all these values that have been given in the question, the uh, question asks us to solve for the oxide capacitance, and we have to find it in the picofarads. So now for oxide capacitance, let us write down this solution. For the oxide capacitance, we know this unit area capacitance, is simply given by the epsilon ox by the thickness of the oxide, that is Pox. Now I will simply put the values of this epsilon ox. The ER is this epsilon R is 3.9, the relative permittivity, and this epsilon for the material is 8.85 into 10 raised power minus 14. So for this oxide, which is Si2, I have multiplied with relative dielectric. So this has to be divided by the thickness, which is in which this quantity is in centimeter units. So this capacitance has this oxide capacitance per unit area requires the thickness to be calculated in the centimeters. Since it's 55 nanometer, it's 10 to the power minus 9 of meters, or it is simply 10 to the power minus 7 centimeter if I take the centimeter units. Now let us solve for this. Simply, if we solve it on the calculator, it will simply be 3.9 into 8.85 divided by 55. So it comes out to be equal to approximately 62.8 into 10 raised power minus 9 farad per centimeter square. But we have been told to find the total oxide capacitance. So this total oxide capacitance, if I write, wait a second, this total oxide capacitance will simply be this oxide capacitance per unit area multiplied by the area. And we know this, let us add some slides. We know the area, wait a second, we know that this capacitance now will be equal to, this is 62.8 into 10 raised power minus 9, and this has to be multiplied by the area. Area is 2 into 10 raised power minus 3. So let us simply multiply this 2 into 10 raised power minus 3. So if I simply multiply it, it should give me approximately 126 into 10 raised power minus 12 farad, or simply it is 126 picofarad. So let us check the options. The option A seems to be the reasonable selection because it was close to 126. Yeah, so we will go with option A. Now it says that for the MOSCAP that was given in question 4, so the data that was present in question 4 will remain as it is. So that MOS capacitor that was given in question 4, we need to calculate the depletion width, that is xt, for the same parameters. Now to calculate the depletion width, we need to have some parameters like the uh, phi f, that is the um, surface potential at which the pinning has occurred, and for that we will assume that the pinning has occurred at 2 phi f. So let us write down the condition for maximum depletion width. The pinning has occurred at the 2 phi f. So depletion width maximum depletion width is simply xd is given by 2 times epsilon s into psi s, and we will assume it to be pinned at 2 phi f. So it is 2 phi f divided by QNA. Now I have to find this phi f first. So this is the Fermi level. We have assumed the Fermi level to be pinned at 2 phi f. Now to find the this phi f, I will simply use, I have to go through the band diagram, and we have seen that how we can find this phi f by just writing the potential balance equations in the previous lectures. So here we will simply write down the phi f that we found in that previous lectures, that was Vt ln of Na by Ni, where this Na is the acceptor concentration and this Ni is the intrinsic carrier concentration. So let me put the values for these. The phi f will simply be 25.9 into 10 raised power minus 3 ln of Na. Let us check Na value. Na is 10 to the power of 16. Okay, it is 10 to the power of, it is 10 to the power of 16 divided by 1.5 into 10 raised power 10, which is the intrinsic area concentration. Now let me use my calculator again and solve this. So basically it is ln of into 25. Right. So basically it will come out to be equal to 0.347 volts. So we have got this phi f. Now we can find this xt maximum. So it will simply be now equal to 2 times epsilon s. 2 into epsilon s is 11.7 for the silicon. That's the relative permittivity. The relative. So we have to take it 8.85 into 10 raised power minus 14, 2 times epsilon s into 2 phi f. 2 into phi f was 0.347 that we got previously, divided by QNA, which is Q is the electronic charge, 1.6 into 10 raised power minus 19, and Na is 10 raised power 16. Let us do the required calculations to obtain the desired values. Wait a second. So it is 2 into 2 into 11.7 into 8.85 into 0.34347 divided by 1.6. So it will come out to be equal to 3 into 10 raised power minus 7, approximately centimeters. So this XD, if I convert it into micrometer, it will simply be equal to 0.3 micrometer. Now let us check the options and we will see that option D is clearly matching our results. So we will go with option D. Now there is same problem associated with that question number 4. It says that for the MOS capacitor given in question number 4, we have to calculate the value of effective capacitance. This time it's unit area capacitance. So it's per unit area. We don't have to take the area into consideration. Now it has been given that the maximum depletion width has been achieved. So at this condition, we will be having two series capacitance. One will be the semiconductor capacitance that will be due to this depletion width, and the other will be the oxide capacitance. We will have the series effect. So this this effective capacitance will simply be equal to C ox into C depletion divided by C ox plus C depletion. So this C depletion needs to be calculated. C depletion is simply equal to epsilon s by xt, and epsilon s is 11.7 into 8.85 into 10 raised power minus 14, and this xd is the maximum depletion rate that we found out to be 0.3 micrometer. 3 into 0.3 micrometer. Sorry, this was 0.3 micrometer. If this was 0.3 micrometer, I directly wrote it over here in meters. I shouldn't have written it in centimeter like this. So it is, if this is 0.3 micrometer, uh, uh, let me go again to it and check the results for this zero point 0.3 micrometer. This is 0.3 into 10 raised power minus 6 meter, or if I convert it into centimeter, it will be 0.3 into 10 raised power minus 4 centimeters, since the above quantity is in centimeter square. So it will be 10 to the power minus 4. Now let me do the required calculations and get the answer. 0.85 into 11.7 divided by 3. So it will come out to be equal to 3.415 4515. Wait a second. 4515 into 10 raised power minus 8 farad per centimeter square. Now we have got the oxide capacitance in question 1. If we use that, we will simply get the desired result, which was 126 picofarad, but that was total capacitance. The capacitance in per unit area was 6.28 into 10 raised power minus 8. So I will be using that. So the C effective will become 6.28 into 10 raised power minus 8 multiplied by this value, which came out to be equal to 3.45 into 10 raised power minus 8. If I now take these quantities, 6.28 plus 3.4515 into 10 raised power minus 8, I will get the effective capacitance by simply multiplying 6.28 into 3.4515. This has to be divided by this sum, and this is 6.28 plus 3.4515. So it is approximately equal to 2.227 into 10 raised power minus 8 farad per centimeter square. So we have got the effective capacitance to be equal to this number. Now let me check the options. So the only option that matches our results is 2.23 10 raised power minus 8. So we are close to this. So we will write it to be like this. This is approximately equal to 2.3 into 10 raised power 2.3 into, wait a second, 2.23 into 10 raised power minus 8 farad per centimeter square. So let's move to another problem, which says that we have been given the CV curve for the MOSCAP, and we have to tell from that CV curve whether the substrate was N-type or whether it was P-type. And also we have to tell another statement, which is that if there is some positive charge in the oxide, if we introduce some positive charge in the oxide, what will happen to the CV plot, whether it will shift to left or whether it will shift to right. So now let us see this question number 3 plot. This plot over here, as we can see that this plot, when we have positive voltages, when the V is positive, when we can clearly see this region, when this V is positive, we are getting the depletion. So what does this mean? This means that this is P-type substrate, because the depletion region will be formed only when we have applied the positive bias for the P-type substrate. And as it's written over here, that this depletion region will not be formed if the MOS capacitor has N-type substrate, but from CV curve, C reduces if V is increased. So we can clearly see that this statement is false. So this statement is false. Now, if we now introduce some positive charge in the oxide and see what will happen to this CV curve. Now, if there are some positive charges that are introduced in the oxide, we will be required less amount of voltage on the gate to modulate the charge in the channel, because this depletion would have already started because of those positive charges that are present in the channel, sorry, that are present in the oxide, and thus the gate voltage we will be requiring less positive gate voltage as compared to the previous voltage that was required when we had zero oxide charges. Now, since we have positive oxide charges, these positive oxide charges will try to uh, equalize the effect, and thus we will be requiring less amount of positive voltage. So that's what it is written. If positive charge is introduced in the oxide layer, then to equalize this effect, the applied voltage must be reduced. Thus, the CV plot moves to the left because now less amount of voltage is required. So if we see, we will be having something like this. Okay, it will move towards the leftwards. Now this shape will remain the same. I'm not doing anything with the shape here. Now let's see another problem. It says that if we have the MOS cap with gate voltage equal to the threshold voltage, we know at this condition the surface potential must be equal to 2 phi f. So it states that we have to look into this and find which of the terms or which of these statements are false statements. So the surface potential is equal to twice the value of phi f. So that's true. So this statement will be remain there. There is no band bending in the semiconductor. This is absolutely wrong. This will only happen at the flat band voltage. That there will be no band bending in the semiconductor. And so this is false statement. So I will write F against this F. Simple. The inversion charge concentration at the interface matches the majority carrier concentration at the bulk. This is absolutely true. The surface potential is phi f. False. It is 2 phi f. So we have done this problem. Now let's move towards another problem. It says that if we have some MOS gap which is in strong inversion, what will happen to the surface charge density? So, as is seen from the plot that is over here, in this strong inversion, there is exponential uh, dependence of this. So, this surface charge density it will increase exponentially as uh, as a function of this surface potential, as is clear from the plot. We will be having this exponential rise in the um, this in the strong inversion for the surface charge density. Now let us move towards another problem. So we will, sorry, we will go with option B because the surface charge potential will have the exponential effect. It will increase it exponentially. Now let us see another problem. It says that we have been given a MOS cap. This is similar to the other problems with p-type silicon substrate. So we have been given this MOS cap with p-type silicon substrate, and this is doped with accepted doping concentration of 10 to the power of 14, and the temperature is 300 Kelvin. Remember, this temperature is important for this thermal voltage calculations. If it had been some different temperature, we would have calculated the thermal voltage at that particular temperature. Since it's 300 Kelvin, and at 300 Kelvin we know it is 25.9 millivolts, and it has been given over here as well. So the oxide heat thickness in this case is 50 nanometer, And the metal semiconductor work function phi ms is given to be equal to minus 0.83 volts. The intrinsic carrier concentration is given to be equal to 1.5 into 10 to the power of 10. So the threshold voltage needs to be calculated for this MOSFET. We can write the expression for the threshold voltage simply. The threshold voltage will simply be equal to phi ms plus 2 phi f plus 2 phi f plus Q depletion by C hours. So we need to find the Q depletion first. To find the Q depletion, let me write down this Q depletion. We will need the depletion width. So it will be equal to QNA XT. So this depletion width needs to be found out. So this depletion width is equal to 2 times epsilon SIS. So let us take the maximum depletion width. So it has happened that the Fermi level pinning has occurred. So we will take it to be equal to 2 pi f. We have taken the Fermi level to be pinned at 2 pi f, and this is Q and A. Now let me find this phi f. Simply let us find this phi f. This phi f will simply be equal to Vt, where this Vt is the thermal voltage, ln of Na by N. This Vt is 25.9 millivolts, and this ln of Na is given to be equal to 10 to the power of 14. So it is given to be equal to 10 to the power of 14, and Ni is 1.5 into 10 to the power of 10. Let us solve this. Let us solve this. It will simply come to be equal to, wait a second, 10 divided by 1.5 ln of 6.66 into 10 to the power of 3 into 25.9. So it will come out to be equal to 0, sorry, 0.228 volts. So this is the phi f. Now from this phi f, let us find this maximum depletion width, which is xt. So it is 2 into epsilon s, 11.7 into 8.85 into 10 raised power minus 14 into the 2 phi f, which is 2 into 0.228 divided by QNA, which is 1.6 into 10 raised power minus 19 into the acceptor doping concentration, which was 10 to the power of 14. Let us solve this. So it will come out to into 11.7 into 8.85 into 2 into 0.228 divided by 1.6. It is 59 point this thing. So if I take its square root, it will come out to be equal to 24.29 into 10 raised power minus 5 centimeter. So we have got this depletion width. Now we can calculate the depletion charge. Let's add some slide. So this depletion charge Q depth will simply be equal to Q Na xt. This is equal to 1.6 into 10 raised power minus 19. Na is 10 to the power of 14. Xt we found out to be equal to 24.29 into 10 raised power minus 5. 24.29 into 10 raised power of minus 5. So this is what we are left with. Let's solve this. and get the charge per unit area. So if I solve this, it will simply be equal to 1.6 into 24.29. It will simply be equal to 38.864 into 10 to the power of minus 10 coulomb per centimeter square. Now, the threshold voltage Vt is equal to phi ms plus 2 phi f plus this q dep by C ox. See, let us write the values for phi ms. Phi ms was equal to minus 0.83 minus 0.83 plus 2 phi f 2 into 0.228 plus q dep is 38.864 into 10 to the power of minus 10. C ox will simply be equal to epsilon ox by T ox. Epsilon ox by T ox. So let me multiply these values. Let me add these values first. 2 into 0.228 minus of 0.83. So it's minus 0.374 plus simply this will be equal to 38.864 into 10 to the power of minus 10. Epsilon ox is 3.9 into 8.85 into 10 to the power of minus 14. T ox is 50 nanometer. So it's 50 nanometer is 10 to the power minus 9 meter or 10 to the power minus 7 in centimeter. So let us solve this. 38.864 into T divided by 3.9, 3.9 divided by 85. So it's 56.3 into 10 raised power minus 3. So let's add some slide. So it's equal to this Vt is equal to minus 0.374 minus 0.374 plus 56.3 into 10 raised power minus 3. So if I add to it this value minus 0.374, so it will come out to be equal to minus 0.32 volts. So let's check our options. Which option does it match? So it is option A that is closest to our calculations. So we will go with this option A. Now let's move towards another assignment, which is assignment 9. This is assignment 9. So we will be dealing with the MOSFET in this assignment. Till now, we have been dealing with the MOSFET. Now this is for the first time we are going to see the MOSFET in our course assignment solved. So this over here, this problem over here states that we have been given an n-channel MOSFET, and this n-channel MOSFET is having some width which is 15 micrometer and some length equal to 2 micrometer. The oxide capacitance is given to be equal to 69 nanofarad per centimeter square. So it has been told for us to assume that this MOSFET is in non-saturation regime with less or low VDS, which is equal to 0.1 volts. So this is small VDS that has been applied. So the drain current is equal to 35 microampere for a gate to source voltage of 1.5 volts, and it is equal to 75 microamperes for a gate to source voltage of 2.5 volts. So we have been told to find the threshold voltage of this MOSFET, and we have been given one hint over here. This hint, it states that we can use the small VDS approximation in the drain current equation. So let me write down this solution. This simply the drain current we can write down the since this VDS is small, the MOSFET MOSFET is in linear region, and the current equation in linear region will become ID equal to mu n, where mu n is the mobility of the electrons, Cox is the oxide capacitance, Cox W by L VGS minus VTH, where this VTH is the threshold voltage that we need to find, into VDS. This is for small VDS. Now there are two conditions. We have been given two conditions for two gate to source voltage, that is 1.5 volts and 2.5 volts, and corresponding to that we have been given two currents. So let me use the first current, which is this 35 microampere when we have VGS equal to 1.5 volts. So this will be equal to 35 microamperes. This is 10 to the power minus 6. Let me write it as case 1. 10 to the power of minus 6 is equal to mu n Cox W by L. This is VGS 1.5 minus VTH into VDS. VDS is zero point 0.1 volt. Let me write it down as equation A. Now there is another condition when we have been given for 2.5 volts, the current is 75 microamperes. So case 2 is 75 microamperes of current. So I will write it down like this: mu n Cox W by L 2.5 minus VTH into zero point 0.1, that is VDS. Let me write down as B. Now, since these quantities are same for the both, so I will divide equation B, dividing equation B by equation A. So I will be left with this is 75 microamperes divided by 35 microamperes, and this has to be equal to mu n Cox W by L. This will be equal to mu n Cox W by L 2.5 minus VTH into zero point 0.1 divided by mu n Cox W by L 1.5 minus VTH into 0.1. This and this will go with this, and we will be having 75 times this 1.5 minus VTH. This will also go is equal to 35 into 2.5 minus of VTH. So it will simply become, if I multiply these quantities, will be 75 into 1.5, 112.5 minus 75 VTH is equal to 35 into 2.5, it is 87.5 minus 35 VTH. So it will be equal to, simply this will be equal to 25 will be equal to 40 VTH. Yes. So if I now divide these two, it will give me 25 by 40, which is 0.625 volts. Let us check the options. Okay, I have not put the options. So this is our answer. So this is our answer. We have got the threshold voltage of this MOSFET, which was given to us. Now let's move to another problem. It says that we have been given a MOSFET. This time it's not the N-type MOSFET. This time we are having the P-channel MOSFET. And the mobility of the holes is going to be equal to 310 centimeters square per volt second. And the thickness of the oxide is 22 nanometers, while the W by L ratio is going to be equal to 60. This time the threshold voltage is given, and it is given to be equal to minus of 0.4 volts. And this transistor is biased in saturation in this time. Previously it was biased in linear region. So now we have the saturation region. So in the saturation region, we will be required to find the ratio of the currents for two gate voltages, that is 1 volt, that is VSG of 1 volt and VSG of 2 volts. We have to find out the ID1 by ID2. Now let us write down the equation. Since uh, this is p-type MOSFET, the saturation current will simply be given. If I write the general expression, it will be simply 1 by 2 mu p Cox, where mu p is the mobility of holes, W by L VSG plus VTH whole square. Now I have two ID sat currents, which is ID1, which corresponds to 1 by 2 mu p Cox W by L, which corresponds to VSG of 1 volt. This is 1 volt, and the VTH for that is minus 0.4 whole square. So this is equation A. Similarly, ID2 is 1 by 2 mu P Cox W by L, and this time this VSG is 2 volts. This is 2 minus of 0.4 whole square. Let us name it as equation B. So let us divide the equations. Dividing equation A by equation B, and we will get ID1 by ID2 to be equal to 1 by 2 mu P C ox W by L, 1 minus of 0.4 whole square divided by 1 by 2 mu P C ox W by L, 2 minus of 0.4 whole square. So this term will go, and we will be simply left with 0.6 whole square divided by 1.6 whole square. So let us solve this. 0.6 into 0.6 divided by 1.6 divided by 1.6. So it will come out to be equal to ID1 by ID2 will come out to be equal to 0.14. So this is the ratio of the currents in the saturation region when of the one of this current was at 1 volt and the other current was at the 2 volts. So we have found the ratio, the desired ratio. Now let's move towards another problem. It says that we have a silicon N-type MOSFET, and for the silicon N-type MOSFET, the width of the MOSFET has been given, and also the length is given. Width is equal to 10 micrometer and length is equal to 1 micrometer. The oxide thickness is given to be equal to 20 nanometer, while as the threshold voltage is 1 volt. The device is biased at some gate to source voltage of 3 volts, and the drain to source voltage is 5 volts. The mobility is given to be equal to 300 centimeters square per volt second, and we have been told to find the region of the operation. So for that, we will first write down the variables that we require. VGS is given to be equal to 3 volt. VTH, the threshold voltage, is given to be equal to 1 volt. VDS is equal to 5 volts. Now, if I calculate this VGS minus VTH, VGS minus VTH is simply 3 minus 1, it is 2 volts. Clearly we can say that this VDS is greater than VGS minus VTH. So the MOSFET is in saturation. MOSFET is in saturation. We have got the desired result. Now let's move to another problem. It has been told to uh, find the transconductance of the MOSFET that is given in question number 3. So we have to find the transconductance of the MOSFET first. For that, mm, let us revisit the MOSFET current equation in saturation. The saturation current equation, the current in saturation for a n-type MOSFET, for an n-type MOSFET is simply ID is equal to 1 by 2 mu n C ox W by L VGS minus VTH whole square. Now this transconductance is GM. This is the transconductance. Transconductance. And transconductance is given by dID by dVGS. So let's take the derivative of the equation, this equation. So if I take its derivative, it will simply be equal to, if I take its derivative, dID by dVGS, it will simply be equal to 1 by 2 mu n C ox W over L into 2 times VGS minus VTH. This 2 and 2 will go, this 2 and 2 will go, and we will be left with the expression for the transconductance. It will simply be mu n C ox W by L VGS minus VTH. This is the expression for the transconductance of the MOSFET. And we found this by writing the equation for the MOSFET in the saturation region. And here we had the N-type MOSFET. Now let us calculate the value for the GM. Let's insert some slides. So this GM is equal to mu n C ox. This mu n is equal to 300, and C ox, for that we need epsilon ox by T ox. So T ox is 20 nanometer. So it is simply epsilon ox is 3.9 into 8.85 into 10 to the power of minus 14 divided by this 20 nanometer, which is 20 to 10 raised power minus 9 meter, or 20 to 10 raised power minus centimeter, into VGS minus VTH. So VGS minus VTH, that we had already found out, it is equal to 2. So this is the GM. So let me calculate it. Let me calculate the value for the GM. This is simply equal to 2 into 3.9 into 8.85 divided by, divided by 20 into 2. Wait a second. It is 300 into 3.9 into 8.85 into 2 divided by 20. So it will come out to be equal to 1.035 into 10 to the power of minus 4. So if I, this is 10 to the power of minus 3, and so this will be in Siemens. This will be the GM. Now let's move to another problem, which says that uh, we have to consider an N-channel MOSFET with the channel length of 1.25 micrometer, and the mobility of the electrons is 650 centimeter square per volt second. The threshold voltage is 0.65 volts, and we have been told to design the channel width of the MOSFET such that the uh, saturation drain current is 4 milliamperes, and the gate to source voltage for that case is 5 volts. The oxide capacitance has been given to be equal to 69 nanofarad per centimeter square. Now wait a second, let us solve this by writing the saturation current equation, which is equal to 1 by 2 mu n C ox W by L VGS minus VTH whole square. So the ID is going to be equal to 4 milliamperes. So it's 4 into 10 raised to minus 3. This is 1 by 2. Mu n is given to be equal to 650. And C ox is given to be equal to 69 nanofarad. So it's 69 to 10 raised to minus 9. Let me take the W as it is, and the L is 1.25. Since I have kept the L in micrometer, I will get the value of W also in micrometer. VGS is simply 5 volts and VTH is equal to 0.65. Now, if I do the calculations, let us do the calculations and find this W by L. It will simply be equal to 4 into 2 divided by 650 divided by 69 divided by 5 nines 6 5 5 6 5 9.426 into 9.426 9.426 into 10 raised power of minus 9 into 10 raised power of plus 9 will be equal to W by L. So this needs to be multiplied by this L. So I will be multiplying this 9.426 by this 1.25 to get the value of W. So if I multiply it by 1.25, it will simply be 11. So the W will be equal to 11.7 micrometer. So we have designed this MOSFET with the W of 11.7 micrometer. So clearly, by giving it a particular length that we had been given, we found out how we can design the MOSFET. Now, previously, uh, we had seen that when we will sweep, we will be having fast sweep, we will be getting the capacitance curve, which was somewhat like this. So it kept reducing as compared to this curve, which was in the case of high frequency. We obtained this curve, another curve, which kept reducing. So we told that this is due to the fast DC sweep. So if this is the capacitance and this is the voltage, so we told this is due to the fast sweep. So by that we mean somebody had asked and I told at that time, but I feel that uh, there is a need for this clarification as I didn't drew at that time, I just spoke. So if this is the voltage that we are applying on the gate and this is the DC voltage and this is the time scale, if I am applying some voltage which is a ramp like this and this is having some magnitude that is A. Now I am applying another ramp. Let me denote it with this color. And this is having more slope. And this is the other ramp that I am applying continuously. So this is the fast sweep. So this is what we mean by the fast DC sweep that we had done to obtain this capacitance curve in the region when we had this when we had to calculate the capacitance, we just swept the DC quickly. And this is what it means, the fast sweep. So this is what we mean by the fast sweep. Now, uh, let me conclude this lecture for today, and we will be solving the rest of the assignment questions for this assignment itself in the 11th tutorial. So thank you for this live session, and hope to see the people in next session. So thank you very much for joining today's session.